In this video, we want to explore primary and secondary surveillance radar. First, we'll look at the learning outcomes. Then we'll look at concepts behind radar and how radar can be used for surveilling aircraft. And then we'll talk about specifics of primary and secondary surveillance radar, particularly the Mode S and Mode C operations of the secondary surveillance radar. We'll summarize what we did and look at what's next. So, upon completion of this module, which is this video and the next video, the student should be able to explain the differences between primary surveillance radar and secondary surveillance radar, and talk about Mode A and Mode C secondary surveillance radar operation. You should state how Mode A and Mode C data are encoded, and then describe Mode S secondary surveillance radar operation and how those data are encoded, and then how we can use that to implement what's called automatic dependent surveillance broadcast. So radar is a World War II technology. It's called radar stance action acronym for radio detection and ranging. And it's good for detection and surveillance that we're going to talk about here. But it can also be used as a radar altimeter. It can be used using the Doppler effect to get an aircraft's velocity. And even before development of inertial navigation systems, you could do dead reckoning using Doppler radar for velocity. And that Doppler property also lets you pick out strength of rainfall and the like. So it's used for weather radar. We're not really going to talk about weather radar or Doppler radar for velocity as much. We just really want to talk about radar for detection and surveillance. So you probably understand the basic radar concept. You transmit a signal, you wait, and then you get a reflection from it, and you can measure the time duration between when you sent your pulse and when you got the echo back to calculate the distance. You can also, again, by measuring the frequency shift, you can determine velocity. We're not, again, going to be talking much about that, but that's the Doppler velocity idea. So there is this idea of a radar mile, and that's the time it takes for a radar pulse to travel and return 1 nautical mile. And that's basically 12.34 microseconds. So every, clearly almost a million times a second, or almost 100,000 times a second. If it was 10 microseconds, it would be exactly 100,000 times a second. You could go back and forth a mile, so light travels pretty fast. So surveillance radar comes in two flavors, the primary surveillance radar and the secondary surveillance radar. And in primary surveillance radar, as shown in the image with the box on the left, you send out a signal and it just comes back, you get a reply. So it's a passive system as far as the aircraft is concerned, it's just sitting there reflecting. In secondary surveillance radar, though, the aircraft has an antenna, it notices it's been pinged by the air traffic control, and that ping comes in on a certain frequency to 1030 megahertz, and then it replies it on 1090 megahertz with a completely separate response. That's a secondary surveillance radar. So it's an active system, and the aircraft has a device called a transponder that manipulates and responds to the interrogation. So you have an interrogation reply model. They're both ground-based systems, even though the secondary surveillance radar Mode S that we'll talk about in the next video can be used for aircraft-to-aircraft information exchange. So primary surveillance radars are situated throughout the U.S. The upper left panel here are weather radars at air traffic control sites. But the ASR-9 and ASR-11s, these are primary surveillance radars. The ASR-9s are the older version. The ASR-11s are newer ones. So that's aircraft surveillance radar. In the table there, you can see under the ASR-9 and ASR-11, ASR-9s were built by Grumman, ASR-11s by Raytheon, and it has, you can see they transmit power megawatts for the ASR-9, 20 kilowatts for the ASR-11, and they send these pulses maybe 1,000 times a second. And they have a beam width and both in elevation and azimuth, and the antenna has a certain gain and the like. and they rotate 12 and a half times a minute. So there's your how fast the thing is that you're rotating. And so you see on the maps the ASR11s and the ASR9s. ASR9s are older systems deployed lots of airports. ASR11s going in more recently at selected airports. There's not many in Florida, as you can see, but there are plenty of ASR9s. It looks like there's one at Daytona Beach. And the paper that I took these images from was really about using a surveillance radar for weather information, and you can get that information back. The other type here, the ARSR, these are in-range radars, and you notice a lot of them are on the coast and on the border, and these may be repurposed military, or they may have been sites that were military at one time. Sort of a common continental defense for NORAD kind of stations there. Looks very, very similar. So surveillance radar, primary surveillance radar, the display is called a PPI, primary plan position indicator. And I'm not quite sure why the plan's in there. But all you see are the blips where which gives you the location, the range, and then the azimuth. The azimuth information coming from where the radar was in its rotation, the range coming from the time of the reflection. So, and the rotating sweep is the classic look of a radar screen. The right-hand panel is a secondary surveillance radar display, and you can see that it's got little icons standing for each aircraft. It's got information about each aircraft, including altitude, who it is. So you can pick out several ones there. The Delta 2054 over there, sort of center left, and the I don't know all the codes for all the different airlines anymore. DAL always pops out at me. So again, it has information about the altitude, heading. You can get other information. We'll find out about this even sort of like where they're coming from and to. Delta 2100 there near the center to the right and down a little. I'm not, I guess that's flight level 3310 and climbing. 477 knots. It's going from Atlanta to Boston, and it's 750. B752 is, I don't know, 757? I'm not quite sure. Or maybe that's just a flight number there. Anyway, you can see there's a lot more information than just altitude or position there. So primary surveillance radars and secondary surveillance radars, you've seen these dishes before. The primary surveillance one is the bigger one. It's got to have more power and it's got to have more antenna gain. Secondary surveillance radar, since again it's not you're gonna use the transmitted signal back from the aircraft, you don't have to have as much gain there. There's these two other antennas that are used for side lobe suppression. We'll talk about how that works into the secondary surveillance coding in a minute. So as we transmit power, the primary surveillance radar, it's going to look to the aircraft. It's far enough away it's going to look like a point source. And you know when you have a point source of energy, you put a sphere around. This is what Gauss figured out a long time ago. You put a sphere around it, and the area of that sphere is going to be proportional to the radius squared. So any energy going through that surface is going to be spread out over something with a radius an area proportional to the radius squared. So the area is going to, as you get further out, you're going to get less energy per unit area of the sphere, and that's what makes the power fall off like a 1 over r squared, because the area of that sphere is increasing like r squared. The reflection is going to act the same way to the receiver now on the ground. It's going to look like a point source. So now you've got a 1 over r squared from the source to the target, and a 1 over r squared from the target back to the source, and so you get a 1 over r to the fourth kind of power for the overall situation. So again, the primary surveillance radar has to be more powerful, and these are signals in the L band, 1 to 2 gigahertz, S band we saw on the previous chart there were some 2 gigahertz. The secondary surveillance radars are 1030, 1090 megahertz, so those are 1.030, 1.090 gigahertz, so those are L-band signals. Secondary surveillance radar is almost a communication system in a way. It's also called ATCRABS, which is Air Traffic Control Radar Beacon System, which is what its original name was. And so you first, let's start with the two modes, mode A and mode C. We'll talk about mode S in the next video. You want to send to the aircraft whether you're doing a mode A interrogation or a mode C interrogation. And so these are encoded through a series of 3 pulses, and it's the distance in time between the first pulse and the third pulse that tells it whether it's a mode A or a mode C. So in a mode A, pulse 3 is 8 microseconds behind pulse 1, and in a mode C, it's 21 microseconds behind pulse 1. Pulse 2 is going to be transmitted, so that's all being transmitted on 1030 megahertz. The aircraft's going to respond on 1090 megahertz. We've already talked about how you tell the difference between mode A, and mode A is called an identity mode. The aircraft is going to respond with its identity, with what's called a squawk code. And the C code is an altitude also. So after it responds with the squawk code, it's then going to return a coded value of the altitude. The mode S is going to have another indicator that we'll talk about in the next video. Pulse 2 and the omnidirectional antennas you saw in that image of the rotating antennas. Pulse 2 is sent by those omnidirectional antennas. So that information, the beam formed by the primary and secondary surveillance rotating antennas there, those are directional, but they have side lobes. They may not be as at right angles as shown in this image here, but they are to the side of the main lobe. And so you send this omnidirectional pulse out by P2. So if you're an aircraft that's being interrogated, as this Swiss Air or whatever that is up there, SAS, is being interrogated, P1 and P3 will be big, and P2, which is being sent out in all directions and is not necessarily targeted towards that aircraft, will be small. So the aircraft knows to respond when P2 is smaller than P1 and P3. On the other hand, if the P2 is larger, so the lower aircraft there is looking at one of the side lobes, and so when P2 is transmitted, that it's not going to be receiving, it's going to be receiving P1 and P3 through the side lobes, which has a lower amplitude than that going out through the main lobe. And so the P2 pulse coming from the omnidirectional antenna will be bigger than P1 and P3. And so the aircraft knows not to respond. So what do these responses look like? When an aircraft responds to a mode A interrogation, it sends back its squawk code, its 4-digit code. And you've seen probably this in an aircraft if you've been in the cockpit of an aircraft, and many embry-riddle students have been in the cockpit of aircraft. They're 4 digits that get, the pilot talks to the air traffic control when they file their flight plan. They get assigned a transponder code, and they queue that up with those 4 digits. And they're octal, so the digits are 0 through 7. And so these are assigned to the aircraft. You can already see a problem here. There's only 4,096 of these possible codes here, and there's a lot more aircraft than that. So it soon became obvious that we needed something in addition to the 4-digit transponder. So this example from the reading, the aircraft transponder code is 4361. So these have an ABCD format. So the A digit is 4, the B digit is 3, the C digit is 6, and the D digit is 1. Each of these is coded as a 3-bit octal number. So the A, which is 4, that means octal, 3-bit octal, octal encoded as a 3-bit binary. You have a 1's bit, you have a 2's bit, and you have a 4's bit. So for 4, the 4's bit is 1, the 2's bit is 0, and the 1 bit is 0. For the 3 in the B slot, there's no 4, 2 is 1, and 1 is 1. For 6, you need 1 plus 2, so you have a 1 in the 4 slot and a 1 in the 2 slot. And then for D equals 1, you have 0 in the 4 slot, 0 in the 2 slot, and 1 in the 1 slot. And these, as you can see in the upper panel here, these bits are interleaved. So C and A are interleaved first, and then B and D with a space in between. The bits are basically 1.9 microseconds apart. There's a pulse, it's a 0.45 microseconds, 450 nanoseconds, and then a 1.45 microsecond gap between. Again, this is all pulse module. This is modulating 1090 megahertz. There's a framing bit that says the message is beginning, and then the various C1, A1, C2, A2, C4, A4. There's a skipped bit there, then B1, D1, B2, D2, and B4, and D4, and then the last framing bit, which is 20.3 microseconds after the first framing bit. There can be an additional identifier code pulse that comes 4.35 microseconds after F2, and that is on when air traffic control tells the aircraft, turn on your identity, and so the pilot flips the switch on the cockpit on the flight deck. The identity bit is set, and so then the aircraft squawks. It repeatedly sends its information. Air traffic control receives it, and when the identity bit is set, then that aircraft is highlighted on the display. The mode C response, we also send a 4-octal digit code corresponding to the altitude. So we send the interrogation response, we send the mode A response identifying the aircraft, and then we send a second word, which is the altitude as a flight level. So as you can see from the image to the right, D1 is not used, and then there's two components to this. C is used, C1 and C2 and C4 are used as 100-foot increments, and then the rest of the altitude is represented as a multiple of 500 feet using, and both of these use what are called gray codes. So we're using the same bits, C1, C2, and C4, but you can see in the graph here, if you look at the chart, if you look at the first 5 rows there, you see how C4 changes, how C changes from 001 to 011 to 010 to 110 to 100 as the altitude goes from minus 1,200 feet to minus 800 feet. So we're starting at a base of minus 1,000 feet, and we're adding minus 200, minus 100, 0, 100, and 200. The coding of the C bits there, that's a gray code. A gray code is a code that changes one bit as you change from one value of a level to the next. So as we go from minus 200 to minus 100, we add the second bit, the middle bit. As we go from minus 100 to 0, we drop the first bit. You can see you go from 011 to 010. So you only have a 1-bit change. This reduces the errors, in fact. The rest of the altitude is represented as increments of 500 feet, and that's encoded by a D2 through B4. And again, that's another gray code, and you can see evidence of that in the D2, D4, A1, A2, A4, B1, B2, B4 columns as you go there from flight level 0 to flight level 1 to flight level 2, etc. Of course, those are all the same 500-foot chunk, but then as you increment up at the next 500-foot chunk, you go from one code to the next. And so the overall altitude is encoded as minus 1,000 feet plus this number that's encoded in B2 through D2, that should say D2 to B4, times 500 feet, and then C1 to C4 for the 100-foot increment going from minus 200 to 200. It's a little bit complicated, but it's a robust way of encoding that information. So in this video, we've looked at primary surveillance radar, which lets us find out the range and azimuth of a target, and secondary surveillance radar, which lets the target send back its identity in mode A and its altitude in mode C. Next time, we'll talk about mode S, or select mode, which gives air traffic control the ability to address specific aircraft, and it also allows aircraft to broadcast their own position, both to air traffic control and to other aircraft. And that's what's called ADSB, Automatic Dependent Surveillance Broadcast.